Okay, Mr. Leong, I heard you have a very high IQ.
You heard right?
Wow, can you impress me with your IQ later?
Sure, no problem.
Okay, so let me give you an IQ test.
Okay.
Okay, so what you see on the screen now are 4 beautiful photos.
Very beautiful.
Yes, indeed, right? So it's our very handsome Mr. Tim.
Okay.
You know, okay, I don't want to say it, but you know, Mr. Handsome Tim, 4
Still looking
photos of
good
him.
lah,
Yeah,
all
looking
4,
good, looking
yes.
good. So can you help me arrange these 4 photos in a particular order? Notice the pattern and
Okay.
arrange it in a particular order.
Okay, so these are the photos, right? I think I will arrange it in this manner. You see?
Interesting way to do it.
Okay.
Can you enlighten me on your reason of doing it?
Sure. So if I take a look on the left photo, right, he is very well dressed,
Okay.
very prim and proper. This is how he looks like at the start of the day, right? So as time passes by, as he teaches more and more classes, teaches more and more of you guys, you notice that that is the end of the day. His state, how he looks like, right? A lot of buttons unbuttoned. He doesn't smell as good anymore, and his hair is unkempt, very disheveled, right?
Yes.
Right. So I think I'm going to arrange him in chronological order for a particular day as a tutor for him.
I see.
Yes. So this, I think I would say that this is an increase in entropy. Now, based on what I explained now, Mr. Yap, can you share with me what do you think entropy really means?
So based on the way you arrange, right? So from Mr. Tim with a prim and proper look to at the end not so proper,
Okay.
more messy. So I would think that entropy means a measure of the messiness of the system,
Right.
or what we call in chemistry term the disorder of the system.
Right.
Okay. Yeah.
So what does it mean about high or low entropy then? So if you look at the left photo, right, he is very orderly. He's very prim and proper. So therefore, we're going to say that he has a low entropy.
Yep.
But if you move as time passes by, the last photo that you see over there, you notice that he's going to have a lot. It's very messy. He's very disorderly. So therefore, we say that he's going to have a high entropy.
Okay.
Right. So therefore, the larger the entropy, the more disorderly there is.
Yes, yes.
Right. So, Mr. Yap, let me ask you a question, right? So, in terms of how easy, do you think it's easier to achieve high entropy or low entropy?
You mean let's go back to the example of Mr. Tim again.
Yeah,
Right?
sure.
So I know Mr. Tim for close to a year.
Right,
Based
okay.
on his my understanding of him,
Oh.
I mean it's easier for him to get into a state of undressed
Right,
than a state of dress.
So he prefers to unbutton his shirt.
Yes,
is that what you
yes,
mean?
yes,
Oh, right. So that is actually consistent with my second law of thermodynamics, right?
Oh.
That for any kind of spontaneous reaction, the entropy would usually increase.
Okay.
Okay, so it's the same thing as like a room, right?
Yeah.
So I hope that you're watching this in a room right now. You look at your surroundings now. Do you think your state of your room is it in high entropy or low entropy?
I mean, I don't have to answer that.
Oh,
they know
okay.
they know the answer in their hearts.
Oh,
So
right,
let's
right,
not
right.
expose them.
Oh, sure. So that is exactly the idea of entropy over here.
Yep.
Now, Mr. Yap, can you run us through a little bit more about the idea of entropy in chemistry terms?
Right. So essentially, once again, entropy, in terms of the definition, is essentially the measure of the disorder of the system. So if we say something has a large entropy or high entropy, it means that the system is very disordered. There's a higher degree of randomness. Okay, and we also say that there are actually more ways to distribute the particles and energy of the system.
Right.
Okay. Now, in this topic, other than the entropy value itself, what we are concerned with is the entropy change, delta S. Now, change is always final minus initial. So if we talk about entropy change of a reaction, we are actually referring to the entropy of the products, subtract away the entropy of the reactants. Now, if the products are more disordered, it has a higher entropy, and therefore we say entropy change is positive.
Right.
Now, conversely, if entropy decreases through the reaction, then the entropy change will be negative. Okay, now let's try to consolidate this with a simple example using the diagram shown on the screen. So this diagram shows the solid particles arranged on the left and the liquid particles arranged on the right. So when it melts, when the solid melts, the particles change from an orderly arrangement to a disorderly arrangement.
Right.
So, Mr. Leong, in terms of the messiness and the disorder, right, obviously the system is getting
More messy.
right. So when the system is getting more messy, the liquid state has a higher entropy, and we say that the delta S is actually positive.
That's right. So of course the converse will be true. If we
Yep.
do freezing, everything will just be the opposite.
Yep.
Now what we're going to do next, right, is going to pay attention to the 4 main factors that affect entropy.
Okay.
The first of which is going to be on temperature.
Yep.
So I think this one is pretty straightforward. So if I take a look at a system where you suddenly increase temperature, right, how do you think the entropy will change, Mr.
I
Yap?
mean, when temperature is higher, the particles, they possess more kinetic energy. They're going
Okay.
to be moving more randomly and rapidly in all directions, right?
That's right.
So the entropy, therefore, will be higher, and we would say that there are more possible energy states, states to distribute the particles. So therefore, entropy change is positive.
That's right. So that will be the first factor.
Yep.
Quite straightforward. Now the second one is going to be a phase transition, or what we call a change of state. The three states of matter is gases, liquids, and solids,
Yep.
right? So in terms of their entropy wise, which one do you think will have the highest entropy?
I mean, what we've seen just now, right? So the gaseous state, the particles are most disordered and most random in terms of their movement. So I would think that the entropy is the highest for the gas.
That's right. So for gases, highest entropy, and this is much higher as compared to liquids and solids.
Yep.
I think the reason is pretty obvious,
Yep.
because gases, they are really random, they are really fast. When you compare it against the liquids and the solids, where they are much more in an orderly state, right? So therefore, the entropy of the gas is much higher than of the liquid or the solid.
Yep.
Now, the third factor that we're going to look at is going to be the number of particles over here. So we'll jump straight into an example, which is using N2O4. Is going to break down to give you 2NO2 over here. So I think in order to understand a little bit more about the entropy change, Mr. Yap, can you share with me an analogy here?
Okay, so I mean, imagine there's a party, right? The party initially only got the two of us, right?
Right.
Sounds like a boring party.
Okay.
But as more people come to the party, right? We're gonna mingle with them. We're gonna have some fun together.
Sure.
So it's gonna get more noisy. It's gonna get rowdier. So in terms of the messiness and the disorder of the system, what do you think is gonna happen?
I think it's going to get more disorderly, which means that the S is going to increase,
Yes.
and delta S will be positive.
Yep.
Right. So with that, we can actually look at this, because the number of particles in the system increases from 1 mole to 2 moles. Of course, you're going to have more ways of arranging the particles, which contributes to an increase in S,
Yep.
and therefore your delta S will be positive. Right.
Yes.
So this is for the gaseous system. Let's look at a second example where we look at a aqueous system. Now for aqueous system, it's going to be the same thing as well.
Yep.
So Mr. Yap, can you run us through this?
All right, so let's look at the left-hand side of the equation first. There are actually 4 moles of aqueous particles.
Yes.
Okay,
And
and
how
on the
about
right-hand side, 7 moles of aqueous particles, right?
Yes.
So 4 moles of particles increase to 7 moles of particles, right? So the system is going to get more disordered. Entropy is higher. Delta S is going to be positive.
Sure. Now, Mr. I'm going to throw you a challenge. Now, let's
Okay.
take a look at the new equation that I wrote over here, the one in blue.
Okay.
Observe this, study this properly, and can you tell me how would the entropy change be like?
Right, so using the same framework,
Yep.
left-hand side, 2 moles of particles.
Okay.
Right-hand side, 3 moles of particles, right?
Okay.
So 2 increase to 3, right? Bigger, right? So entropy is higher. Delta S is going to be positive.
Okay, unfortunately, this is wrong.
Oh no.
Okay, why is that so? So here, turns out there's additional information that must pay attention to. So if I take a look at the states over here, right, you notice that there's going to be a difference in the state
Okay,
symbols.
yes, yes.
Some of them are gaseous, some of them are aqueous.
Yep.
So in terms of the different states over here, right, just now earlier we mentioned that the one for the gases is going to have the highest entropy. Now this implies the fact that every time if there's a change in the number of gases, right, that will actually affect the entropy change the most.
Yep, okay.
So this means that I'm going to correct your understanding a little bit.
Okay.
Instead of just looking at the change in the number of particles, right, what is more important is actually look at the change in the number of gaseous particles.
Okay.
So using this new theory, this revised theory, can you change your answer as well?
So I mean, now if you're asking me to focus on the gaseous particles, on the left-hand side, there's only 1 mole of gaseous particle.
Okay, there's only one gas moles,
Yes,
right?
and then right-hand side, there's 0 moles of gaseous particles.
Okay.
So there's a decrease in the number of moles of gaseous particle. Entropy is going to drop. Delta S is going to be negative.
That's right. So at the end of the day, when you look at any chemical reaction, the first thing that you should always focus on is the change in the number of gaseous particles, right? After which, if it's no more gases, then you look at the next most will be the liquid and will be the solids eventually.
Yep.
All right, the last one that we're going to look at is going to be of mixing of particles. So using the diagram over here, let's say I have 2 boxes, one of which is red particles, the other is going to be a white particles. And if I want to mix them together with an increase in volume, I'm going to experience an increase in the entropy,
Yep.
right? So Mr. Yap, another analogy, please.
Okay, analogy. Now, Mr. Leong, do you like to play soccer?
Not really, no.
Do you watch soccer?
No.
Okay, good.
Okay.
Now, so if you focus on the left box, which contains the red particles, let's say they are Liverpool players, right,
okay.
standing on one half of the soccer field.
Right.
Then the white particles are Tottenham players, standing on the other half of the soccer field.
Right.
Now, when the referee blows the whistle and the match starts, right, the particles can mix, so the players are starting to kick some balls around, right? So they're going to
Okay.
play the game of soccer.
Right.
So they are mixing together. So you would think that they are going to be more disordered, right?
Okay.
Right. So therefore, the entropy is higher.
Oh, wow. Mr. Yap, looks like you're really a huge football fan, huh?
Actually, I don't watch soccer at all.
Oh, okay, can. Good analogy. So coming back to the chemistry part of it, you notice that every time you mix two particles with an increase in volume, then entropy is going to increase. So a classic example over here is what happens if you add a solvent into another solution. So if you add solvent, number one, you're going to experience an increase in the volume, and number two, there's going to be more particles, which also corresponds to more ways to arrange all your particles inside the new solution.
Yep.
So of course, your entropy is definitely going to increase.
Yes. Okay, Mr. Leong. Actually, you're talking about all these factors.
Right.
It's a bit dry.
Oh, you need some water?
No, I don't
okay.
want water.
Oh.
So let's spice things up a bit.
Oh, sure.
Okay, I heard you are afraid of heights. Right?
Am I? Okay.
So how about we go for bungee jumping right now?
Okay, sure. Let's go.
Huh? Hey, why you agree so readily? Why are you so spontaneous?
Whoa, 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 whoa. This coffee is cold already. Hey, intern, help me buy a new cup of coffee, please.
Coffee 小弟搞不松冰半烧打包咖啡快啦。
Okay, good, good, good. Okay, while waiting for my new coffee to come, Mr. Yap, let's talk a little bit. Okay, let's talk about some chemistry.
I thought you meant to talk about life.
Chemistry first lah.
Okay.
So if I take a look at this cup of coffee
Okay.
cooling down,
Okay.
it is a spontaneous process. But can you tell me a little bit more about its entropy then?
I mean, the temperature decreased, right? The coffee cooled down, the temperature must have decreased. So I would say that the entropy decreases, the entropy change is negative.
Oh, okay. That sounds a little bit weird, right? Because
Okay.
if you have a negative entropy, how could it be a spontaneous reaction? Normally, if you want a spontaneous reaction, the entropy will usually increase.
Okay,
So why
yes.
do you think that is so?
Good question. So I mean, there must be another factor that comes into play
Okay.
when we talk about a spontaneous reaction. There.
Sure.
Yeah.
What kind of factor do you think this is?
I mean, this topic is about energetics, right? So this is
Okay.
the part 2 of the topic. So
Right.
I believe I need to use some concepts taught in part 1,
Right.
which is the enthalpy change, delta
Okay.
H.
Okay.
So this coffee is cooling down. This cooling down process is what we call an exothermic reaction because
Okay.
heat is released to the surroundings.
Okay.
So it's an exothermic cooling process.
That's right. So now you realize that spontaneity of a reaction is actually dependent on two very important energetic
Yes.
terms, right? One of which is enthalpy, the other one is going to be entropy.
Yes.
So to group them all together, I think we would like to collectively call it a new energy term
Okay.
called the Gibbs free energy change, which is denoted by delta G over
Delta
here.
G, yes.
Okay. So ultimately, delta G is going to be the main indicator for spontaneity of a reaction.
All right. So spontaneity simply means when we say something is spontaneous, when a reaction is spontaneous, we mean that the reaction can occur on its own without an external driving force. You don't need to pump in any energy or whatsoever. It will just happen on its own.
Right.
Now, in terms of the value of delta G, if delta G is a negative value, I know it's a bit counterintuitive, but if delta G is negative, we would say that the reaction is spontaneous. It will happen on its own. Now, if delta G is positive, it's the opposite. The reaction is not spontaneous. You need to pump in energy to drive the reaction forward.
That's right.
Okay. Now, a common misconception that students will have here is this. So they will always think that a spontaneous reaction means the reaction occurs very quickly. But that's not true. A spontaneous reaction simply means that the reaction can occur on its own without external driving force. It does not tell you how fast or slow the reaction occurs. So spontaneity is not equal to rate.
That's right. So we mentioned earlier just now that delta H and delta S, right, are the two main factors affecting spontaneity. So we accumulate in this thing called the delta G. So it turns out there's going to be an equation that relates them all. And it's
Okay.
given over here for me. Delta G equals to delta H minus T delta S.
Okay. So Mr. Leong, this looks like a bit complicated for me and my math not very good.
Oh,
So can you give me a shortcut? Because you're a man of shortcuts, right?
sure. So we have G, the letter G.
Okay.
We have H. We have T and S. What kind of word do you think we can use to connect them together?
Let's play the game again.
So the word is ghost.
Oh, okay.
So if I take a look at this, delta G is equals to delta H minus T delta S. So obviously the letters are swapped. The O has no meaning lah. So it's just a shortcut for you to remember this the formula a bit better.
Okay, but Mr. Leong, what if the student is scared of ghosts?
Okay, then moving on, if I take a look at this formula, one of the important things to pay attention to is the units of the equation, right?
Okay.
So first things first, you must understand that delta G always has the units of kilojoules per mole, and you realize that from the previous chapter, delta H also has the same units, right?
Yep.
Now, the second part over here, there's a T. Now, this T is what we call the absolute temperature,
Yep.
and what is the units for absolute temperature?
Kelvin.
Kelvins, right? And because of that, the units for delta S will be a little bit different,
Okay.
right? So I'll derive this here for you. Now, in order to match up to the left-hand side having the units of kilojoules per mole, your delta S must definitely have a kilojoules per mole over here, right? Okay, but you realize that the delta S is multiplied by a T whose units is K. So, Mr. Yap, can you suggest for me, what do you think I should do to the K, what should I do to the units so that I can get rid of the K, so the units matches up to the left-hand side?
So K must be multiplied by the inverse of K for it to cancel out. So
That's
K
right.
minus 1.
That's right. So this will be the units for delta S.
Yes.
Okay. But one warning here, you will notice that if you look at questions or if you look at literature values, right, delta S is usually not given in kilojoules per mole.
Okay.
They usually give you in terms of joules per mole per Kelvin instead.
Yep.
Right. So Mr. Yap, can you tell me how to convert into kilojoules?
I mean, maths is not my strong suit, but
Okay.
I would think that joules to kilojoules must be multiplied by 1000.
You are correct in the way that your math is not good.
Okay.
So actually it's not multiplied by 1000. From joules to kilojoules, you have to divide by 1000. Okay?
Okay.
So that's something that you must pay attention to as you do the calculations in class.
Yep. See you guys. Okay, can you say see you guys?
See you guys.
Okay, see you guys. Bye-bye.